Let's take a look one more time at f of x equals sine of x over x. You'll recall we discovered that even though it's not defined at x equals 0, because we would have division by 0, we would have 0 over 0. Even 0 can't be divided by 0. So it's not defined there, but a limit exists as x approaches 0, and that limit was 1. And so if only we had a function that was defined to be 1 at that point, then it would be continuous. But it's not continuous because it's not, f of 0 doesn't exist, so it's not continuous at 0. But if we could write a function, if we could do something about that function and define it to be 1 at 0, then this function would be continuous. And so we're going to look into the concept of a continuous extension at a point where it's otherwise not, a function would not be continuous. And so we could extend the domain to include x equals 0 by defining a new function f of x, capital F of x, where f of 0 equals 1 and f of x equals little f of x, the sine of x over x, everywhere else. And so now our function value for f of 0 equals the limit of the sine of x over x as x approaches 0. The limit is x approaches 0 of sine of x over x. And f of x is continuous at x equals 0. So here our new function is a piecewise function. Please note the mistake in your notes. You're going to need to turn that into a 1. Sorry for the typo. And so f of x equals sine of x over x, where x does not equal 0, otherwise it equals 1, where x equals 0. And this is a continuous extension of f of x equals sine x over x. So now let's look at a more in-depth explanation of this continuous extension to a point. So if a function is not defined for a particular value, so say for example division by 0, causing it not to be defined there, then it is often possible to define a new function that defines the missing value. If f of c is not defined, but the limit as x approaches c, we have a limit there, and that equals some value of f of x, and that equals some value L, does exist, then a new function can be defined by making a piecewise function. F of x equals little f of x, big F of x equals little f of x if x is in the domain of f, and otherwise L if x is equal to c. So note that capital F of x is continuous at x equals c, and so we would say that f of x is the, capital F of x is the continuous extension of f to x equals c. Let's look at an example on this. Another example. In example 12, we're going to show that this function, f of x equals x squared plus x minus 6 over x squared minus 4, for x not equal to 2, has a continuous extension to x equals 2, and we're going to find that extension. So let's take this function. Remember, when we're trying to find limits, we're going to have to be able to have a limit there at x equals 2. And so let's take and figure out what the limit as x approaches 2 would be of this function. So first of all, we would want to simplify that function if we can. It's not going to have a limit if that's a vertical asymptote. It will have a limit if x equals 2 is just a whole and not a vertical asymptote. And so when we factor those, we find that x minus 2 is in the factor in the numerator and the denominator, so it cancels. So we're left with x plus 3 over x plus 2, and so we find that we would have a limit there. And to find the limit, we would simply plug in the value of 2 into this function, and that would give us 5 over 4. So the other thing we find, though, is now this function, if we let that equal our capital F of x, would be defined where x equals 2. Still not defined at x equals negative 2, just like this one wasn't, but it would be defined at x equals 2. X equals negative 2 would be a vertical asymptote, so it didn't work here and it doesn't work here. But it is defined at x equals 2, and so letting f of x equal x plus 3 over x plus 2, now our function value here at x equals 2 is going to be 5 over 4, which was the same thing we got for the limit. And so now we would say, since f of 2 is equal to the limit as x approaches 2 of f of x, then capital F of x, being defined as x plus 3 over x plus 2, is the continuous extension of f of x to x equals 2. And so now we've found a way that we could redefine it so that this new function would be defined over the entire domain, even though this original one is not defined. The little f of x is not defined at x equals 2.